Hi there. Today we are going to discuss non-homogeneous linear differential equation. We are going to cover two methods, method of undetermined coefficient and method of variation of parameters. We will go over some example problems and provide you with a practice problem. Non-homogeneous linear differential equation has this form. As you can see, the non-linear a linear homogeneous differential equation is defined with this, and non-homogeneous comes because of the Rx being not equal. So as you can see in this differential equation, it's a linear differential equation, but right hand side of the equation is not equal to 0, and that makes it non-homogeneous differential equation. So this equation has a solution of this form where YHX happens to be the solution of homogeneous differential equation, meaning you would solve this problem as if Rx was equal to 0 and you will find out YH. And then for YP, it is going to be determined based upon the type of function that Rx is. And we'll try to use in some ways the information that we have from the homogeneous equation to come up with the YP. So in fact, for non-homogeneous differential equations, the focus that we have is mainly determining this YP function, the particular solution for non-homogeneous differential equation. So the first method that we have is called as method of undetermined coefficient. This is useful when we have Rx as a simple function. It could be sine, cosine function, exponential function, or x to the power n. So for example, if it happens to be the x to the power 2, so you're going to have k0 plus k1x plus k2x. If it happens to be e to the power lambda x, then you will have some coefficient times e to the power lambda x. So what we do once we have determined the form, of YP, we take this YP and substitute it back to the actual differential equation. We will take the derivative, second derivative, and put it back into the differential equation to find out these constants. And once these constants are known, we have the YP. And YP is known, then the general solution happens to be YH plus YP. Two things to note. If a term in your choice of YP happens to be similar to, for example, if it happens to be the same as the term in your homogeneous differential equation solution, then we have to multiply that with the x. And if it happens to be a double root problem, then we have to multiply it with the x square. And the second thing to note, the right-hand side Rx function doesn't have to be one function. It could be set of functions. It could be addition of multiple functions. If that happens to be the case, you will find out YP1, YP2 for each of the term. Meaning, say, for example, if you have two terms, you'll find YP1 and YP2, and then you will add them together to get the YP. So again, if you have multiple term, the step process still remains same as long as the terms are having this form. They have exponential sine, cosine x, or x to the power. Let's find a general solution of this simple differential equation. Please note these example problems are intentionally made very simple just to focus on the steps to solve the problem. So the first step to solve the problem would be writing down the characteristic equation for homogeneous differential equation, which is lambda square plus 1 equals 0. And we can solve lambda, it equals the square root of -1 or 0 plus 1i. It's a complex root problem, meaning we are going to have the solution of the homogeneous differential equation is going to be of this form: a cos x plus b sin x. Again, it is cos x sin x because omega happens to be 1 in this case. Now, since we have the homogeneous solution, now we are going to focus on the YP, the term that comes from the non-homogeneous component. So by looking at the homogeneous solution, what we see, the solution has cos x and sin x. Again, that's what we have on the homogeneous solution. Now 8x, obviously it has nothing to do with sin x cos x, so we don't have to worry about the two special cases. Now 8x function that we have, it is very similar to so for the 8x, what we have to do, we have to look back into the table, and what we see, this is a form kx to the power n. K happens to be 8, n happens to be 0. So we are going to have k0 plus k1x. And again, that would be the only two terms. If it was kx square, then we will have more terms. It will be additional k2x square and so forth. So now the YP is going to be of this form, k0 plus k1x. Now, as we discussed earlier, we are going to take this function, takes its derivative, second derivative, and put it back to the original differential equation. We will take the derivative, the second derivative, and now we are going to put it back to this equation to find out the constants. And if I put it back, what we realize, k0 must be equal to 0 and k1 must be equal to 8. Now we have the yp equals 8x. We have YH and YP. So general solution is going to be simply adding these two solutions, YH and YP. And the general solution for the entire differential equation is going to be this. Now let's move on to the second method. As we saw, method of undetermined coefficients is limited to certain forms of Rx. It has to be simple functions. Otherwise, that method doesn't work. But method of variation of parameter is more general, and it is also applicable to the higher order ODEs. It doesn't have to be limited to second order. We can use any order ordinary differential equation we can solve using this method. But obviously, this method is a little bit more complex in terms of the steps involved. And that's why the method of undetermined coefficient is choice of method if functions are simple. Otherwise, we have to rely on the variation of parameters. So as per this method, the yp can be expressed like this. It's a summation of yk, wk over wrdx. So what is w here? W is called as a Wronskian. So if y1, y2, yn, again, depending upon the order, if it is nth order, you will have n y's. If it is third order, you'll have 3 y's. If it is second order, you'll have y1 and y2, right? So for example, if it is third order differential equation, Wronskian is going to be defined as this. It is going to be 3 by 3. Again, for second order, it will be 2 by 2. Again, if it is fourth order, then you'll have 4 by 4. So what we do to write the Wronskian, the first row is y1, y2, y3, since it is third order. And then you do the first derivative, second derivative, it becomes a 3 by 3 determinant. And opening it up will give you the W, the Wronskian. Whereas W1 is going to be simply replacing the kth column with 0, 0, 1. In this case, first column, you can replace with 0, 0, 1, and you will get W1. To get W2, you can replace the second column. And to get the W3, for example, you can replace the third column with 0, 0, 1. And once we have the W values, we can write the YP depending upon the order of equation. If it is first order, second order, it will have 2 terms. If it is third order, it will have 3 terms. So these terms are going to be, if you open it up, is Y1, W1 divided by W RDX, and Y2, W2 divided by W RDX integral, and so forth. Let's apply that to a simple example. So the general solution, once we find the YP, the general solution is going to be YH plus YP. Let's apply that to a simple example. We need to find the general solution of this equation, where R, the right hand side, happens to be sec x. Again, it's not a standard function from the table that we saw earlier, so we have to rely on method of undetermined coefficient. Sec x is 1 over cos x, as we all know. Now the first step is obviously trying to find out what is the homogeneous differential equation solution. Like we did in our previous example, the homogeneous differential equation solution is going to be c1 cos x plus c2 sin x. Now, once we have the homogeneous differential equation, we look at the function and find out what are our basis of solutions. In this case, basis of solution is cos x and sin x. So y1 is going to be cos x and y2 is going to be sin x. And we are going to develop a yp based upon these basis of solutions. So y1 is cos x and y2 is sin x. So again, we will find the Wronskians, and then we will use the formula that we had to find out the yp. So we will take the derivative, first derivative for y1 and y2. Since it is second order differential equation, we only need to take the first derivative. And the Wronskian is going to be, again, y1, y2, y1 prime, y2 prime. And then you open up the determinant and you get it equals to cos square plus sin x square x, which happens to be 1. We can find out W1 and W2 by replacing the first column and the second column with 0, 1. And it happens to be minus sin x cos x. Once we have this, we go back to the actual formulation and find out yp. So yp is going to be y1 an integral of w1 divided by w, which is 1. And the rx function is 1 over cos x dx. Same thing, y2, w2 divided by 1, that is w, rx function, and then dx. As we can see, cos x cancel. So this is going to be integral of dx, which happens to be x. And this side, we have a sin x over cos x, which is tan x. So we can rewrite it as minus, take the minus out, minus cos x tan x dx plus x sin x. And then taking the integral, we get the yp as minus cos x ln sec x plus x sin x. Now we have the yp, we already had the yh, we can add them together and we will have the general solution for the entire differential equation. Now we have the constants C1 and C2. This can be determined based upon the given initial conditions if that was given into the problem. Now, one important point to note, whenever we are trying to find out YP should not have any constants. We should determine those YP constants using differential equations like we did before. So again, YP should be just a function where as constant should be only in the YH. And as you can see, this differential equation would require two information to solve it, one in terms of the function and another one as a derivative. We have two practice problems for you. The first problem you are going to solve using method of undetermined coefficient, and the second problem we are going to solve with the variation of parameters. I hope you found this useful. See you next time.